Okay, so this is the final version of splitting that we're going to look at. And again, we'll start with our CH3, but this one's going to be slightly different this time because if, like we've done with the previous examples, we look at the CH3 and then look at the adjacent protons, then in the previous two examples, obviously we looked at CH, then a CH2, the next one up is a CH3. So this will be looking at the splitting observed by these three protons here. However, hopefully you can see the line of symmetry. This molecule would be symmetrical, which actually gives us one of the first things which we don't see in high resolution. When we have symmetry within a molecule, the spectrum gets more simplified, because these three protons on the left, this is a symmetrical molecule, and so these three protons, the CH3 here, is essentially equivalent to the CH3 on the other side. And so what you can't get is splitting from equivalent protons. We don't see that situation. So what we'll do is we'll just remove two of these protons to start and go back to essentially the one we looked at when we looked at the doublet situation. And what we'll do is we'll look at the splitting observed on the CH peak highlighted, but this time we'll look at the splitting which is observed by the CH3 next door. So if we go straight into looking at what the permutations of the three protons we have adjacent, we have obviously three protons available. So we can have one proton going upwards, the other one going upwards, the other one going upwards. Okay, so that's one permutation we've got, again obviously aligning ourselves with the magnetic field. We then have a situation possible whereby we can have one proton going downwards, and because we have three different protons, it is possible to have the downward proton being the middle one, the other two going up. So we have two going up, one going down, but it's possible to have three different versions of that permutation because of the availability of you having one, two, or three different protons within the group. So that's statistical. There is then also possible to have similar situation, but essentially the reverse. So we have two groups going downwards, and again we have the three possible situations whereby two are going down and one is going up, and then the final one is the situation whereby all of the protons are pointing downwards. But this time we can now see the heights of the peaks that would then be observed. We have one possible variation of that, we have three variations of this, three variations of this, and one variation of this. So if we jump straight into the peak this time, without looking at the low resolution version, we can see that the peak observed when we look at the CH here will be split into a quartet of peaks, whereby the area under the curve, remember the curve is the entirety of all of the split peaks, so the area under that curve is equal to the integration of the proton we're looking at, which in this example is just one hydrogen's worth of integration because we're looking at this proton, remember, but it is split into a quartet. Okay, so it's split into a quartet with integration heights of 1, 3, 3, 1, due to it being adjacent to a CH3. Remember, that's being adjacent to a CH3. The peak itself is due to the CH, but the shape of the peak is due to the protons on the adjacent hydrogen. And what we'll do is we'll summarize that in the next clip and get the overall rule, which is called the N+1 rule, summarized.